Hello, my name is Kyle Dedke.
And I'm Tyler Williams.
And I'm Austin George. And for our senior project, we worked with a company called Melford Borzall and took one of their new products, which is currently fabricated, and redesigned it as a casting. Okay, so a brief agenda of what we're going to cover in this presentation. First, we're going to give you a background on the company, and then move into the project background. Next, we'll talk about the current design issues that Melford is facing with their product, and then go into our redesign process, the prototyping, and then finally the testing and future production of the new product. First, we're going to give you a little bit of background on the company we work with. Melford Borzall is a manufacturing company in Santa Maria, California. They design, manufacture, and distribute drilling and boring heads primarily for shallow horizontal directional drilling (HDD) applications such as running water or cable lines. Next, we're going to give you an example of a typical HDD process. Here is a simulation of a typical HDD process. First, a drilling head is used to create a pilot hole. After the pilot hole is finished, the bit has to be removed, a process that requires a lot of time and effort in a very confined space. A reaming bit is then added in order to backream the hole while pulling the line back through. Although this is necessary in applications where a larger hole is needed, there are many situations where the pilot hole size is sufficient and a lot of time is wasted by changing the bits out in order to pull the line through.
We met with Melford Borzall and they presented us with a new product that they were hoping to introduce but was still in the early stages of prototyping and testing. The part, named the Eagle Eye, acts as an attachment to their highest selling product, the Eagle Claw. This new product would eliminate the need to detach the Eagle Claw and attach a reaming bit in applications that do not require substantial back reaming. This attachment can quickly be added to the Eagle Claw and used to pull the line through the bored hole. Here's a CAD assembly for reference showing the current production Eagle Eye attached to the Eagle Claw. Note that this stage would occur after the pilot hole has been drilled, and the line or tubing to be run through the hole would be attached at the end of the bracket opposite the Eagle Claw. However, there are some issues with the current design of the Eagle Eye. These are some of the main issues. The Eagle Eye is fabricated from 5 separate components which are welded together. The welding process creates heat-affected zones, which results in inferior metallurgical structure and weak points. The individual parts are plasma cut from sheets of steel, which leaves sharp edges where stress concentrations can form. There have also been failures occurring at the bolt hole area as well as at the welded joints where the gussets meet the main body. Another issue that has been highlighted is that the part is not as aesthetically pleasing as is desired by Melford Borzall to increase sales of the Eagle Claw.
So essentially our problem statement is as follows. Melford Borzall wants the Eagle Eye attachment redesigned for casting. The new design should perform better, be more aesthetically pleasing, and cost less to produce than the current fabricated design. These are the requirements that we had to keep in mind during the redesign phase. We went through multiple design iterations that addressed issues with casting apart while still trying to increase the strength of the existing fabrication. In our research, we found that castings tend to be stronger than their fabricated counterparts. We received multiple feedback from Melford before we settled on a final design. Here's an animation of our final design. There were multiple design considerations we had to follow during our redesign. First being that the part must have a uniform wall thickness. Second, to add fillets and rounds to reduce stress concentrations. Third, since this was going to be casted, a shrink factor had to be incorporated, and if we were to go the route of a sand casting, draft angles would have to be used. Melford also wanted the casting to fit in the pre-existing fixture for post-process machining.
Here we can see a side-by-side comparison of the original design versus our new design. On the left, you'll see the original design, which is comprised of the pole base, the pole body, the gussets, and carbide inserts. The 4 labeled parts are plasma cut out of sheet steel and then welded together. The carbide inserts are then brazed in after the machining processes are complete. One of the most noticeable changes in our design is that of the gussets. On the original design, which can be seen on the left, the gussets are rather small and must be welded in place. The welding is difficult to keep consistent, resulting in variation from part to part. This could result in inferior performance or significant wear to the part. As previously mentioned, the welding of the gussets also creates heat-affected zones which lead to weak spots. The sharp corners where the gussets meet the body also allow for considerable stress concentrations, something that we want to avoid, especially given the fact that this is one of the areas that Melford Borzall is currently seeing their design fail. On the right, you can see that the gussets are much larger and provide a nearly seamless transition from the back of the pole base tapering into the pole body. This adds a significant amount of material to the eagle eye and will greatly increase the strength of the gusset area. Another significant change can be seen around the pole base. On the original design, the amount of material between the front of the pole base and the bolt hole is minimal. This thin section is a definite area of concern due to the fact that this is where a large amount of force is applied during use. This is another area that Melford has seen their part failing. In order to combat this issue, we added as much material as was feasible to both the front and back of the pole base. This adds strength to the bolt hole area and should reduce the tendency for the part to break around this feature. The larger gussets will also help to reduce the amount of force concentrated around the bolt hole by helping to alleviate the bending moment that may occur. Here you can see another side-by-side comparison showing the old and new design attached to the Eagle Claw. We had to be careful during our design process to ensure that the new part would mate correctly with the Eagle Claw. As you can see, the Eagle Claw has a number of carbide studs or inserts around the body. We had to ensure that our part did not contact or interfere with any of these bits. We tapered the gussets as far down on the rear of the pole base before they directly contacted the carbide bits. One of the most limiting constraints was that the Eagle Eye pole base mates with a slot machined into the Eagle Claw. This slot is 1 inch wide, and therefore the width of the pole base could not exceed 1 inch. But because we wanted to add material around the bolt hole, we had to get creative with our design. We added an angled step to both the front and back of the pole base, which allowed the Eagle Eye to mate properly with the Eagle Claw, while also adding the desired amount of material to strengthen the part. Next, we will take you through the prototyping process.
After our design had been finalized and accepted by the stakeholders at Melford Borzall, we created a 3D printed version in order to verify the fit of the part on the Eagle Claw and to make sure that it engaged the mating surfaces properly and did not interfere with any of the carbide bits. In the picture on the right, the 3D printed part can be seen mated with the Eagle Claw. Once fit was verified, we continued development with a cast prototype. Here you can see one of the 10 cast prototypes. These prototypes were created by first creating a 3D pattern using the stereolithography process. This pattern was then used to create sand molds, which were poured at a foundry in the Los Angeles area that we had a contact at. We were assisted by an engineer at this foundry in the design of the gating system. The cast parts were then shipped to Melford Borzall for post-process machining. The next stage of the process included research into testing methods.
Currently, Melford Borzall does not have a standard testing procedure in place for their products. For the most part, they verify their new designs by giving parts to local drilling companies to try and field. Although this field testing method provides Melford Borzall with some feedback about the performance of the part, it doesn't give them any details. For this reason, we wanted to conduct research into some testing methods that would provide Melford Borzall with valuable data about the new part. In regards to our newly designed part, Melford wanted it to handle an applied load of 20,000 pounds and achieve a yield strength of 100 kSI. Given these values, we decided that a simple tensile test would allow us to verify that these desires were met. We reached out to Instron, a company that manufactures a variety of testing machines. Instron provided us with a list of all the testing facilities located in California. After contacting various facilities and collecting quotes for the testing of several of the original parts as well as the new prototypes, this information was given to Melford Borzall, and they are currently deciding if this is the route they want to go with testing. The final step after testing is to make a decision on the future production of the part. The two casting processes that are candidates for the new design are sand casting and investment casting. The fact that this part has some unique geometry makes finding a parting line somewhat difficult. The sand casting process requires a clear parting line, and although it would be possible to sand cast this part, it would not be the easiest method. Another consideration is the surface finish of the part. Melford desires parts with a nice surface finish in order to appeal to their customers. Investment casting provides much better surface finish as well as dimensional accuracy, while also eliminating the issue of identifying a parting line. The part also needs to be cast with the pull eye included in order to reduce the need for post-process machining. Sand casting would require the inclusion of cores, which adds complexity and cost, while investment casting can achieve this without complications or costs. For these reasons, we believe that investment casting would be a more viable option for future production, despite the addition of costs for the production of hard tooling. We reached out to several foundries and received quotes on investment casting. The quotes showed that the parts could be poured for around $100 a piece, and that the cost of tooling would be paid off in approximately 6 months with Melford's current production level of 200 parts annually. This information was provided to Melford Borzall, and we are looking forward to see what they ultimately decide to do concerning the full-scale production of our redesigned Eagle Eye. Thank you for taking the time to watch our presentation. We look forward to answering any questions you have.